this one right here. So the slope of that line, you go up 2 over 2, so it's y equals x. And then the y-intercept here is negative 2, so x minus 2. So I'm going to write this down. Y equals x minus 2. So y is 1/2 u minus v equals x, which is 1/2 u plus v minus 2. Multiply everything by 2. And then notice the u's cancel. I'll move my v's to one side. Negative 2v equals negative 4. So v equals 2. So v equals 2 over here. Like this. And then I'll do the same thing for this line segment here. That again has a slope of 1, has a y-intercept of negative 1 though. So if I come over here and change this, the only thing that changes is this is a minus 1. This is a minus 1, and when I multiply both sides by 2, I get 2 here, which gives me negative 2 there, and then minus 2 there, and then here it'll be 1. So v is 1 is my other line segment here. And it's the region bounded by all 4, so it should be this region right there. And that may not look like a better region, okay, but I think our integration is going to be easier. So would you look at this as a type 1 or a type 2 region back from the integrals when we first started doing double integrals? Well, type 2, right? Because I draw an arrowed segment there, turn my head. This one is always, as I move this up and down, this function always stays on this side of the arrow. This one's always on the bottom side. And my v values are between 1 and 2. So I know v goes between 1 and 2, and my u's are between 2 functions of v. This one right here is u is v. So the one on the right is u is v. And this one right here is v is negative u. If you solve that for u, it's u is negative v. So this is negative v. So it's stuck between those two. All right. What else do we need? I have my limits of integration. I have how that's going to switch over. Now I need the Jacobian. So let's get the Jacobian. Jacobian is going to be this, which equals partial x with respect to u, partial y with respect to v, minus partial x with respect to v, is partial y with respect to u, without going through all that work again. Partial of x with respect to u is going to be 1/2. Partial y with respect to v is negative 1/2. Minus partial x with respect to v is 1/2. Partial y with respect to u is 1/2. So you get negative 1/4 minus 1/4, which is negative 1/2. So I'm ready now to rewrite the double integral. This double integral I'm going to go du dv, because v has limits 1 and 2. U has limits negative v and v. And then I'm integrating e to the u over v. And then I need the absolute value of my Jacobian. Negative 1/2. Absolute value. That's positive 1/2, and that can come out. So 1/2 integral 1 to 2 integral, well, yeah, integral negative v to v. E to the, I'm going to write that as 1 over v times u, and then du dv. And the reason I'm doing that is because I'm about to integrate that with respect to u. And when I do that, I'm going to treat v like a constant. So 1 over v will be a constant. So this is 1/2 integral 1 to 2. Antiderivative of e to the 1 over v u is going to be v e to the 1 over v u. So just think about it. What's the derivative of this with respect to u? That's a constant. Ignore it. Derivative of that is itself times the derivative of what's up here with respect to u is 1 over v. So 1 over v pops out, hits that v, goes away, and that would leave you with this. So that's the antiderivative. Evaluating from u equals negative v to u equals v. And then I'll integrate with respect to v. So this is equal to 1/2 integral 1 to 2 of, let's see, plug in v for u, and you get 1 over v times v, that's 1. So you get v times e to the 1, so v e to the 1, that's fine. Minus, and then now plug in negative v, you get v e to the negative 1, and dv. All right, next step. Just remember e to the 1 and e to the negative 1 are constants. So I'm going to go ahead and take an antiderivative now. Antiderivative of this with respect to v is 1/2 v times e to the 1. Antiderivative of this with respect to z is minus 1/2 v. I forgot to put v squared, sorry. V squared e to the negative 1. And I'm evaluating this from v equals 1 to 2. So let's let v be 2. 2 squared is 4. Half of 4 is 2. So I get 1/2 2 e to the 1. Now when I plug in 2 here, I get the same thing. Minus 2e to the negative 1. Okay, that's what I get when I plug in 2. Minus 1/2, let's plug in 1. So you get 1/2 e to the 1 minus 1/2 e to the negative 1. Now let's distribute this through. This 1/2, you get e to the 1 minus e to the negative 1. Let's distribute this through 1/4, but then you're subtracting, so minus 1/4 e to the 1, and then this is going to be minus 1/4, but then plus, so plus 1/4 e to the negative 1. And you can combine these two together and these two together. So you get e to the 1 plus, or yeah, e to the 1 minus 1/4 e to the 1 is 3/4 e to the 1. I'm just going to write as e. And then negative e to the negative 1 plus 1/4 e to the negative 1 is minus 3/4 e to the negative 1. This is the same as 3/4 e minus 1 over e. All right, that's it for that. So I do a couple of these on homework, but now I'm going to take a little bit more time. I want to show you where, if you recall, whenever we were doing conversions from Cartesian to polar coordinates, right? If we had a double integral over some region R of f of x, y, dA, and we wanted to go to polar, we would go double integral over some region, I'll call it S, f, and what we did is we replaced x with r cosine theta and y with r sine theta. And then we said we always had to put this r in there. And then it was either like dr d theta, or it might be d theta dr. But we said, you know, this r had to be there, and tried to explain a little bit where it came from. But what I want you to see now is that this is actually the Jacobian, okay? It's the magnitude of the Jacobian. And so what I'll do is I'm just going to convince you of where that r came from. What were our transformations? X was equal to r cosine theta, and y was equal to r sine theta. Now, I could have written x is equal to like u cosine v, y is equal to u sine v. So I could have used u and v, but we used r and theta because geometrically the r and the theta made sense. So I'm going to stick with r and theta. So the Jacobian is going to take xy over to r theta. And so that will be this determinant, partial of x with respect to r, partial x with respect to theta, partial y with respect to r, partial y with respect to theta. And then by definition, this is partial x with respect to r times this, partial y with respect to theta minus this and this, partial x with respect to theta, partial y with respect to r, which is, well, what is the partial of x with respect to r? So what's the derivative of this if we treat r like the variable and theta like a constant? It's just going to be cosine theta times partial of y with respect to theta. So this time r is a constant, theta is a variable, derivative of sine theta is cosine theta, but I have an r in front of it, so r cosine theta. I'm running out of room. Let me do that over here. So where are we? We're at cosine theta times r cosine theta. Then we say minus, what's the partial of x with respect to theta? So what's the derivative of this with respect to theta? Well, the r comes along for the ride. Derivative of cosine is negative sine. So I get negative r sine theta. And then the partial of y with respect to r. So I'm treating now theta like a constant. There's my variable. Derivative of that is just going to be sine theta. And when I clean that up, I get r cosine squared theta plus, because I have two negatives, r sine squared theta. And if I take out an r, factor out an r, I get cosine squared theta plus sine squared theta, which is 1, and so r times 1 is r. So your Jacobian, you take the absolute value of that, you just get r. So, well, absolute value of r is just r because r was the radius, and the radius we're going to assume is positive. So that's where the r comes from in polar conversion, which is pretty cool. Now, last section, and this is probably the hardest thing to show you. It's going to take a while, but in the last section, we did spherical. And remember when we did spherical, we always had to throw something into that triple integral. Remember, it was rho squared sine phi. That was that thing we had to throw into the triple integral any time that we went from Cartesian to spherical. So I'd like to show you where that one comes from. So what you have to do is first remember what was the conversion that we used in spherical. Write them down, make sure I got them right here. Our conversions for spherical are x equals rho cosine theta sine phi. Y is rho sine theta sine phi. And z is rho cosine phi. Those were our conversions. So in order to I'm trying to prove to you that this was the Jacobian. The Jacobian